So I would like to introduce our speaker today. Yubai Yuan is an assistant professor of statistics at Penn State. Welcome, Yubai. And Yubai's research focuses on complex network analysis, causal inference, and optimal transport with the application to neuron dynamic study. His other research interests are community detection, link prediction, mediation analysis, active learning, crowdsourcing. Well, thank you, and let us welcome Yubai.
Okay, let me first share my screen.
Okay.
Can everyone see my screen?
So I will stop my share maybe.
Oh, okay, yeah. Can you see my shared screen?
Yes.
Okay, great, perfect. First, I would thank Mosaic and the BERD seminar for inviting me to have the opportunity to present our kind of ongoing and almost finished project. So this is about inferring the diffusion structure, okay, on the network. So this is a joint work with Yuan, a graduate student from Penn State Department of Statistics, and Adil, PhD student from our political science department. Okay. So really this kind of a project is motivated by some idea that, so as a statistician, I think we have a lot of fancy model to construct and to basically identify how actual network data are constructed. So I think, I think we do not have focused too much on study kind of process over network work. For example, once the network is fixed or generated, how the dynamic process over the network look like. So this is really one motivation why I initialized this project. So in this project, we're basically focusing on the pattern of cascade behavior over network. So cascading behavior is actually a very common phenomenon on networks. So like in social media, right? You have the information cascading. So you basically tweet some information, your friends or followers will retweet the information. And also in a pandemic, this is also a very nice example. So the virus basically spread out over different countries and different cities. And also there are kind of in social studies, social science, political science, people tend to want to identify the diffusion pattern about some innovation, technology, and the policy. So you see actually the cascade behavior is basically very common in our real application world. So basically the cascading behavior can be generalized like a process over time on network. So typically you will have some a source node. Okay, this is kind of a zero patient. And it will trigger the similar behavior on other nodes over their interaction. Okay, typically the interaction can proceed over some network. And then you can see, at T0, we have one original node, the zero patient. And then he or she will trigger the other a subject in the following T1 time point. And then you see this process continue. So this is basically like a branching trees, okay, over the timeline. And so in this process, okay, we have some property typically for the so-called cascading behavior. The first one is that typically we can only observe when and where the nodes get infected or get activated. Typically, we cannot observe how they are activated. We don't know who is actually the source that inactivates this node, right? So this is for example, in epidemic, okay, we can have a measurement on how many people are already infected, but we can barely notice the affection pathway among this population. And the other point is that this cascading behavior over the network, it's typically not consistent with the observer network. Okay, so this have two meanings. The first one is that in social media, like Facebook, you typically can have even hundreds of friends. Okay, you are connected in Facebook, but it doesn't mean that you will be equally affected by all these friends, right? You will definitely only affected by some of your important friends. Right? So in other words, this influence is kind of a subset of the observed social network. On the other hand, there's also some unobserved network, right? Some like hidden relation, social relation, do not capture by like Facebook network or your social network, right? You have like social, like individual relation. So in these two says that the network that's cascading diffuse over is not consistent with the observed network, the static network. And another part of for the property of cascading behavior is that typically we have a high missingness in the cascading observations. We cannot like we do not observe typically all the population and their like cascading outcomes. So in summary, we can basically treat the cascading behavior problem as something at the state structure as following. So typically we have a timeline, okay, starting from 0. And we have like a group of population. We just denote as nodes. So we have like here A, B, C, D, E, F, G, something like you can indicate like a person or like a website or like a subject. Okay. And we have like a repeated cascading samples over the same population. Okay. So for example, in the cascade 1, we observe that the node A, okay, he infected or activated at time 0. And then we observe that the node B get activated or infected, and then node C. So we can only observe when the node are activated on timeline. Okay. And similarly, we have another cascade sample 2, ACDE, and cascade samples 3, okay, on BDEF. And also we have some like a time window. Typically, the time window is not like infinite, so we can only have the partial observation. In other words, we have like censorship in this kind of observation. So like in the first cascade, okay, beyond the time window D, we can only know that the DEF is not infected yet until time T. We don't know whether they will eventually infect it. So this kind of a data structure summarizing the cascading behavior we're facing. So this is what we can observe typically from the data.
Well, Yuba,
Yeah.
may I ask, so what is
Sure.
Cascade 1? Is that the
So,
Cascade 1 is A?
the A?
A, yeah.
Oh, this A, we say this is kind of indicating a node on the population or node on network. So you can imagine there's several nodes in a network. So we just index them by A, B, C, D, E, something. And we are just saying that in the first cascading sample, we observe that the node A get infected at time 0. And later, the node B also get infected. Okay. And then node C. Yeah, this is the observed cascading samples. Is this clear, or I can explain, try to explain in a clear way? Yeah? Okay. Yeah, just feel free to like ask if you have any question or like some part unclear. Okay.
Can I ask one question?
Oh yeah, go ahead.
I just wanted to ask like how the time T is decided. So it's
Oh, that's a really good question. The time window T, right?
yeah.
Typically, this is in observational study. Okay, we cannot like decide what is T. This is like the intrinsic property of data, right? You can, for example, like if you collect the social media data, typically you will assign a time period. You would like to collect data like within 1 year, within 1 month. So this is like by design. So you can choose this T, and based on your like source and the computational power, you can choose the T. So typically the larger T is better, right? But typically you have this trade-off between the observation, the sample size, and the source you have. Yeah.
Thank you. Another question is like you said that like DEF was not unobserved by that time T. So that means that they would have been observed later if the T was greater, right?
Yeah. That's what the sensor mean. We don't know it. So the DEF probably will eventually get infected, but they are not infected within time t. So we just their activation status is unknown to us.
Thank you so much.
Yeah. Okay.
So hi, Yubai, I have
Yeah.
another question. So do you know which nodes are connected, which are not? Hello?
Seems frozen.
Yeah.
Yeah,
Is it my internet?
Not you. Seems like you, but the screen is frozen.
Oh,
Dr. Yuan's screen got frozen.
I think, yeah, my level is okay, but Yuba seems to be frozen.
Is a
Must be Penn State level is not doing well.
yeah, I suspect so.
Oh, no, he's moving. Right? Yeah, I think Penn State changed the network recently. And I think like last week, one speaker had there's a visitor to our department who had problem with the network too. So
I believe we have been given until June 30 to move to register the devices on EduRoam or something.
mhm. So what about you? You repeat, are you home or are you at school?
No, I'm at home. I have my
Oh, you
wife.
are at home. Yeah, I'm at home too.
Yeah,
So I think it's the Penn State level.
yeah.
But we will just like take a short break.
Yeah.
Yeah, relax. Okay.
hi. Yeah.
Hi.
Sorry. Yeah, my internet. I don't know why it's kind of just stuck. Yeah.
Yeah, seems like Penn State level has some problem. Like
Yeah, I think
in
so.
this
Yeah.
past few days. Like
Okay.
last week, I think last Thursday they have problem.
Okay. Yeah. Can you see my
Yes.
slide right now? Okay. That's
Yes.
yeah. Maybe we can. Yeah. Yan, I remember you have a question. Sorry. Sorry about that. Interrupt.
Oh,
Yeah.
I actually just have two clarification questions.
Yeah.
So Cascade 1 to Cascade 5, they have nothing to do with each other, right? It's just
They're
five
independent. They're
examples.
independent. Yeah.
And the other question I have is, do you assume the network connections are observed or not?
Not observed. That's what we try to infer. Yeah.
Okay.
Yeah.
Thank you.
Yeah. That's a good question. So Yeah, so this is the observed cascade samples we have. So as Yuan said, so our task is basically try to infer the network connection among these nodes. Basically, this network connection describe how the diffusion go over all the nodes on the network. Okay. So it seems that we have no hope to recover this network structure. Okay, but actually, let's see a motivating example. Suppose there's some Mark Zuckerberg, right, posted some very shocking news, and all the websites start to tweet and retweet this kind of a post. Okay, like starting from CNN, then the Guardian, Fortune, Business Insider, and other website. Okay, so you can see the pattern is that the activation time or the transition delay, like between two websites, really informative in telling us about the intensity of influence between two websites. Okay, so if we can observe, remember we have this a repeated cascade sample. If we observe that the website J and the website I, okay, they frequently post a similar same news, okay, in the same time. And it's kind of a strong evidence to say that maybe there's strong influence between J to I. Okay? So this kind of similar to the intuition of grandeur causality. So if you can use one time series to predict well another time series, so that is kind of information, okay, in this case, kind of influence between these two nodes. So this is really the motivation of the whole methodology. We try to capture the time lag, the transition delay, okay, between two nodes, okay, in cascade behavior. And that a time lag, this delay will tell us about the intensity of between their influence. And because this transition delay is random, okay, so every sample can have different kind of delay. So we of course need a statistical model to quantify the uncertainty. So typically we here, for example, denote this the time lag, being the delta Ji. Delta Ji is the time when the node I get activated minus the time point where node J get infected. So the difference is the time lag. So basically we're gonna utilize a distribution to quantify sorry, the uncertainty of this time lag. And here we're gonna introduce a parameter called alpha Ji. So you can consider this alpha Ji is kind of a transmission rate or the speed, okay, for the cascade diffuse from node J to node I on average. So you can think about this kind of alpha Ji control the shape of distribution of the time delay. So if the alpha Ji is large, then you can imagine that the average, the transition delay is going to be small. And if the alpha Ji is small, then the time lag going to be large. Okay, so eventually, if in the extreme case, if the alpha Ji is 0, then basically there's no transition from J to I, right? So that's the extreme case. So eventually, the goal is actually you can actually try to consider collect all these alpha Ji together as a matrix. Okay? And each alpha Ji, alpha J describe the influence from node I to node J. So now you basically have this kind of graph. And the first thing, this graph is a direct graph, meaning that the alpha Ji can not be equal to alpha Ij, which means the influence can be not symmetric, right? So of course, this is common in social media, right? The two people, although they are connected, they can have different influence to each other. And if the alpha Ji or alpha Ij being 0, as we mentioned, this basically indicating there's no transition from J to I. So in this context, you can infer this that there's no influence from J to I. Okay. So our goal, or the goal of infer the diffusion network, is try to infer the hidden diffusion network structure on the left side from the right side, observe the cascade samples. Okay. So this is our basically the framework of this problem. Okay. Just let me know if you have any question. Okay. So to be more specific, this already have some pioneering work. Okay, so basically the idea is to utilize the survival model in statistics to modeling this kind of transition delay. Okay, this is a very fascinating idea. So suppose we first introduce this called survival function. Okay, you can see the survival function depends on 3 elements. The TJ, this is the time point where the node J get infected. And the TI, this is the time point where node I get infected. And of course, the transition rate, alpha JI. So this survival function basically measures the probability that the node I not infected by J until time Ti. So this kind of, you can think about this kind of survival process, right? The start to J already, sorry, the node TJ, node J already infected, and this node tried to infect node I, but it fails, okay, until like a time point Ti. So this is kind of a survival function part. And correspondingly, you can define the so-called hazard function. Okay, this is the F. Oh, sorry, I forgot about to introduce the F. The F basically is the likelihood where the node I get infected at the Ti, given that the node infected by node J. Okay, so you can define this hazard function as a ratio between this likelihood of infection divided by the survival function. Okay. Then you can also build in other like counterpart in this survival model. But the most key components in this model is this hazard function and the survival function. Okay, as long as you identify these 2 parts, then all the other parts are already identifiable. So basically, this is the survival model we try to use to quantify the uncertainty behavior for this time lag between the 2 nodes. And also there's some different option. Okay, you can use different parametric form you can use for this transition delay model. So this is some kind of, I just list some like common model people tend to use. The first 2, like exponential model and a power law model. Okay, so basically, you can see this kind of time delay kind of exponentially decay over this like alpha Ji, this like a transition rate. Yeah. Oh, sorry, this like time, yeah, transition rate. So the first 2 exponential and power model typically people used in modeling the behavior over social network. And the last relay model, okay, people use that a lot in epidemiology survival model. Okay. But the key part is that you can observe that all this hazard function, they're actually a linear function in terms of this alpha Ji. This is a very important property for all this parametric model. Okay. Another important observation, you can see here, all this kind of distribution of transmission delay is unimode mode. There's only 1 mode in this distribution. Okay, so later we're gonna try to generalize this by our proposed model. Okay. And then previously we just described the distribution model, okay, for describing the time lag between 2 nodes, right? And then we now need to building on this block to construct the distribution of how a node get activated by other nodes. Okay. So here we basically consider a modeling assumption. Okay, so basically a node can be activated once the first parents activates it. Okay, what does this mean? Basically meaning that a node have a lot of parents. The parents meaning that this node already get infected. Okay, and there's 1 node can activate this node I. And based on this kind of assumption, we can actually construct the probability of node I activated by, for example, node J, okay, as something like this. Considering here, in this example, we have 3 nodes already activated, J, K, L, right? They can all be the parents of the unactivated node I. So let's consider the case where the J is the truly parents activated I. Then you can just write down this like a probability likelihood as 3 components. Okay, the F part, this is as we mentioned, this is the probability or the likelihood I get infected by J at the Ti, right? But you need the other 2 component part, meaning that both node K and node L have not affected the node I, okay, before node J, right? So that's it. So the node I survived from node K and node L, but the node I get infected by node J. So this is basically how we modify this event. Okay. Okay, I'll just go through it. And another part is that, of course, each of these parents can be the real parents. Okay, this is actually what's the so-called independent cascade model. The independent cascade model just saying that for all the parents, they can be the first parents of node I. And this and all this event, they are disjoint to each other. So we just sum up the probability of these events separately. Okay. So for example, still in the previous example, we have a JKL. Then this is the probability that each of JKL can be the first parent of node I. You just sum up the previous probability. Okay. So you can see now we have this kind of distribution model to quantify when the node I gonna affected. If there's some, if this node had parents, okay, JKL. But there's another situation, as we mentioned, you have this time window. So what if this like node I never affected, okay, never get infected by all the parents nodes? So this is actually in the last equation. Okay, in this case, you can see then we just multiply all the survival function. In other words, this node I survived from all the parents, okay, the infected parents within the time window T. Okay. So this is just the two situations when we try to modeling the infection time of node I. So far we just already build up this like distribution model, okay, for this like infection time. And now the remaining part is like kind of straightforward, right? Then now you have n nodes in this network. Then you just multiply all the individual probability together. Okay, so now this is have like a probability of TC. Let's just denote this TC as the cascade sample C. Okay, one cascade sample. And now this is the probability or likelihood for one cascade sample. And as we mentioned, typically we need the repeated cascade samples, saying we have like capital C number of cascade samples. And typically we assume they are independent, right? There's also some like generalization work saying what if they are not dependent. But in this case, let's just say they are independent. Then you just multiply them together and you will get this like a log likelihood for all the observed cascade samples, okay? As we mentioned, the task is to estimate this diffusion network, this alpha, right? So we just use the MLE estimator with some constraint. Of course, we require each of the transmission rate to be non-negative. Okay? This is a natural requirement. So far, this is how the previous work, okay, dealing with this kind of inference of like diffusion network structure from cascade samples. And in this project, okay, we try to apply this kind of method in application of knowledge diffusion. Specifically, we try to study how the knowledge diffuse over the university in US. Right? This is kind of interesting and also important like question, because once we knowing how the knowledge diffuse over the US university, we can basically understand how some research idea or some like topic, okay, spread over different institutions. And maybe we can identify some like influential university, okay, and how this influential university shape this kind of diffusion, knowledge diffusion. And also maybe we can use this like identify the pattern to check if there's some early detection of hot topics, right? Some like popular topics. And also, of course, like for policymakers, it's kind of helpful for them to make like a policy on funding and research resources. Okay. And in this like study of knowledge diffusion, okay, people already find that there's like two driving factors about this diffusion of knowledge. The first one is the geographic proximity. Okay, this is natural. So it's like we close to UPaid and Penn, right? So there's a lot of interaction, in-person interaction to communicate the research idea, student interactions, common seminar. So if the two universities, they're just close, okay, they're in the same state, then of course they may have strong influence to each other in terms of this knowledge diffusion. But beyond that, there's also some like interesting study about there's so-called invisible colleague or weak ties. So this is like some like a hidden diffusion network connecting the university based on like if like one PhD graduate from the university, this PhD student gonna find a job like in the West Coast, right? So then he will bring this like some research topic from East Coast to West Coast. And also there's some if they tend to some conference or seminar in another location, and in the location they will like in the seminar they will exchange the research topic. So there's some like a lot of hidden interaction on this knowledge diffusion, cannot captured by this geometric relation. So we try to kind of study how these two driving forces affect this knowledge diffusion pattern, or specifically how to shape the diffusion network, okay, in this example. So the data set we're using, okay, this thanks to Adil. He spent a lot of time to clean this massive data. So basically, we're gonna download about like 30,000 journal articles from top 23 like sociology journals. Okay, so in this case, we studied the knowledge diffusion in sociology discipline. And we need to first do some like knowledge alignment. But the basic idea is that we need to remove the redundant topic and calibrate the topics in different papers. Even like the same idea, same like research topic can have a different name, different phrase in different like papers. So we need to first align them. And then we need to identify the university, okay, in this network. Specifically, we identify about 104 university. And this university, first, we are listed in the American Sociology Association, 1965, basically meaning that this university already have sociology graduate program until 1965. And also we need to find the university that's ranked on the list of like a US News Best Sociology Program ranking. Okay. So we find the overlap between these two sets. So that allows us to identify totally 104 universities. And now we also construct so-called geographic network, right? So this is the kind of binary symmetric network. So if the two universities, like University I and J, they are from the same state, like Penn and Penn State, and then there's a one, okay, AIJ meaning one, meaning that they're in the same state. Okay, this is how we construct the geo network. Okay, so this is kind of setup. And another part in this kind of data construction is that we need to connect, okay, the topic diffusion, okay, to the university. Because you can see here, each university, University I, can have a lot of publication, okay, on one same topic. So how we identify the so-called like the infection time of one university. So here we just list, okay, we first find all the first author, okay, whose affiliation is University I, okay. And also we keep final down to the papers that with the same topic, for example, topic C, okay, written by these first authors. Okay, then we have a kind of list of like a publication time. And we just use the earliest publication time on the same topic written by the scholar affiliated with University I as the infected time of University I by these keywords, by this like research idea. Okay, so that is a one-way kind of approximation for the infected time for this like research idea diffusion. Okay, and now then we can basically construct one cascade sample, okay, related to a topic C as T1C, T2C. So basically T1C meaning that this is the infection time of the first university starting to doing the research related to the topic C. Now we have this kind of sequence of time points. Okay. And eventually you can see we get this like a matrix, a really large matrix. Okay, so this is like the number of row is the number of topic. Okay, so far I think we have about 30,000 topics, unique topics, and the number of column is the number of university. In this case, we have 104 university. Okay, and basically the number, okay, the entity in this matrix is the time interval between the publication time, right? The time lag, as we mentioned in the previous method. So we're gonna just like try to infer the diffusion network, okay, based on this like large time lag matrix. Okay. And but here, this is our observation, right? So on the left side, this is the histogram, okay, for the publication time lag. Okay, I just pick up 2 specific examples. So in the first one, so this is the publication time lag between UPenn and Penn State, and on the left side, the bottom left figure, this is the publication time lag between Florida and FSU. So you can see the points that the distribution of publication time lag is not unimode. It's actually have like multiple mode. Okay, so you compare with this observed empirical distribution with the right side, which is suggested by the traditional parametric or homogeneous model. You only have one mode in the distribution. Okay, so in other words, they are not aligned to each other. Okay, so in other words, you have a lot of like hidden diffusion pattern, cannot captured by this unimode homogeneous model. Okay? And in other words, the GeoNetwork itself is not sufficient enough to explain the observed diffusion patterns. Right? If there's only one diffusion pattern explained by GeoNetwork, then we're gonna expect that there's only one mode basically on the left side, right? But now we just give some example. Definitely it's not a homogeneous model. And we just find that this is not unique in this specific application. So the heterogeneity on the cascading behavior is kind of is common. Right? So this is several examples. So people already find that in infectious disease, like technology adoption, okay, and even in finance market, okay, the cascading behavior is not like homogeneous. In other words, there are a lot of different patterns, okay, under the same network about the diffusion about diffusion pattern. So this is another example. This is the figures I like adapted from another paper. This is about like the social media. So when one website posted a news, what's the time lag for the other website post the same news. You can see even in this social media, okay, the time lag distribution is never unimode. You can see here, there's actually a multiple mode in this social media application. So this is actually the main motivation for us to consider about the proposed model. So the model we're gonna propose here, try to address this kind of heterogeneity. It's called double mixture cascading model, okay? Actually, it's not that, it's kind of intuitive. So let's recap first. So the time, TIC, this is the node I get infected, okay, in Cascade C. So basically, this kind of follow a distribution, okay, dependent on this alpha I. This alpha I is just the ith column in the directed diffusion network, okay? So you can see in the previous homogeneous model or existing method, people typically assume this alpha, this directed diffusion matrix, they are fixed, okay? And it doesn't change across different cascading samples. So now in this case, we try to generalize this to consider double mixture model, saying that now for each node and each cascade samples, we're introducing an indicator, okay? We call this network indicator. So that is ZIC. So ZIC, they basically independent sample from some kind of Bernoulli distribution. So this ZIC, you can consider this is kind of indicator variable. So if the Z being 1, meaning that, so this diffusion gonna go over the first network, we call that the theta, okay? And if the Z being 0, the diffusion, the cascade will diffuse over another network, we call psi, okay? So here we have 2 networks. And basically, the column of this directed diffusion network is kind of mixture between the column of theta and psi. And the mixture depends on this network indicator function. So this network indicator variable follow binomial distribution with parameter pi I. The pi I, you can consider this kind of preference, okay? For this node I, will it prefer to diffuse more over the network theta or the network psi, right? This is really the preference. Which network the node gonna engage in the cascading behavior, okay? So you can see later why we can use this kind of mixture model to capture the heterogeneity. So now you can see for this cascade C, this is the corresponding diffusion network, right? This is actually the column-wise mixture between the psi and the phi, right? We have two diffusion network, and the lambda is kind of a mixture between them, okay? But it's column-wise mixture. And based on this column-wise mixture, the things we can model is actually shown in these figures. Basically, we allow the one cascade sample to diffuse alternatively between two layers, right? So for example, we have 6 nodes, and starting the cascade starting from node 1, and for the node 2, okay, the node is decided in this case to get the cascade in the first network, okay, the network phi, for example. And then in the second time point, okay, the node 3, okay, can decide to get this like cascade through the hidden network, okay, because the Z3 is 0, right? And for example, node 4 and node 5, node 6, they have flexibility in deciding which network, through which network they get this cascade. So you can see actually we allow this cascade behavior, cascade sample, to jump back and forth between two networks. And you can see because this kind of a combination of all this like network indicator for each node, the possible number of possible different diffusion patterns is exponential to the exponential to the number of nodes, right? So in other words, although we only have introducing two, like a base diffusion network, through their mixture combination, we can model a very complicated diffusion pattern, okay, over the cascade samples. So this is actually the kind of key intuition for the proposed mixture model. So the reason we call this double mixture, because traditional mixture model, okay, you only have like one index, but here we can see this Z, they are different in terms of both the nodes I and the cascade C, right? So this you have like a degree 2 flexibility. So we call this kind of double mixture model. Okay, so based on this like a double mixture modeling, then we can still write down the likelihood, okay, corresponding likelihood. Now you can see the model depends on both theta, psi, and the pi, right? The pi is the preference of network. Okay. And then we can still similarly write down the likelihood for one cascade sample C, okay, still building on this phi, theta, and the pi. Okay. And this is kind of a first question naturally asks, okay, this seems to be very flexible. It's even identifiable from our data, right? So this is kind of a basic theorem, meaning that as long as the column theta and the column psi, as long as they're not identical, totally identical, okay, this model can still identify the theta and the phi, okay, from the data. Okay, this is actually the first property. But so far, there's no guarantee that the phi and the psi, okay, these two diffusion network can be globally identified, okay? Because you can see here, there's no information can be used to differentiate this theta and the psi. They're basically totally symmetric, okay, in this model. So to allow us to identify this theta, okay, and the psi, we need to pose some like another structure, okay? The first structure, we can pose it on the theta. For example, this A, if you still remember, this is our geo network, right? So we just require that the support of this psi is only on this like geo network, okay? If there's no connection between two universities geographically, then the corresponding influence is just gonna be 0. So in other words, we just require this theta only explain the diffusion pattern over the geo network, over the geographic information. Okay. And then we also need to pose another structure constraint on psi. Okay, this like you can consider this psi as some latent diffusion network. Okay, and we pose some like a rank constraint. So we require that the rank of this psi is slower than some number alpha. The alpha can be much slower than the number of total nodes. And the psi basically captures some like information not explained by the geo network A. Right? So in other words, we would like this psi and the theta to capture some complement diffusion information in our model. And the good part is that if after we compose this kind of structure on theta and the phi, okay, so both of them become global identified. We can basically distinguish, differentiate the phi and the theta in our model based on the data. And there's also some like a rationale, okay, beyond mathematical rationale, why we pose the low rank structure on the latent network structure side. So this is basically due to the very famous like Johnson-Lindros-Strauss lemma. Okay, so you can consider the psi network, latent network, capture the distance, okay, between two nodes in terms of their hidden individual factors. Okay, so if like xi and xj, they're just some like unknown factors of node I and node j. And basically the phi j is proportional to their distance. If they're closer to each other on these latent factors, they have strong influence, right? You can think about like this. Typically the xi and j, they are unknown and they can be high dimensional. But based on this lemma, okay, you can have an arbitrary dimension for this xi, xj. But we only need a small dimension, okay, R is basically log of the number of total nodes. We only need this low dimensional subspace that can preserve this distance on their latent factors. Okay, so in other words, a lot of like large scale network, maybe social network, they always like approximately low rank. Okay, in reality, so that's a kind of intuition why we also pose this low rank structure on this like function. Yeah.
Yes, we have only 10 more minutes. So
okay.
Can we
sure.
Get to the example?
Yeah, sure. Yeah, that's then just quick. We just utilize the constraint EM algorithm to solve our estimation about the theta and the phi. Okay, this is just some like details. I just give it. So let's directly go to the application example. So this is interesting part. So as we mentioned, we utilize the Cascade samples about the research keywords, about 3,000 of them. And we study the diffusion network among 104 universities. Okay. So this is the first part. This is the inferred, the phi, basically, the theta, okay, the diffusion network based on the geo network. Okay, so you can see, of course, they're based on the closeness in the geographic closeness. You can identify several clusters in California. They have like strong interaction, and in the like a Midwest, like in the lake area, okay, also they have like strong influence, like the diffusion of the keyword research idea, and also on the West Coast. Right, this is kind of expected, right, based on the geographic information. And this is actually the so-called the hidden diffusion network. Okay, so in this network, you see there's a lot of coast-to-coast connection. Okay, from East Coast to West Coast. Oh, I forgot to mention here the node stands for different university. Okay, and the size of this node basically is proportional to the out of degree in this network. You can consider that if the nodes have larger size, meaning that they have kind of stronger, have like a larger like a total transmission rate to other university. Okay. So you can identify some like a key university, okay, from these figures. Okay. And we also do some like distribution comparison. Okay, so if we check the distribution of the transmission rate in this theta function and the psi function, okay, you can see this kind of a geo network typically tend to have a strong transition, a large transmission rate, but typically sparse, right? The number is kind of, the frequency is low. But for this, on this latent diffusion network, so each individual transmission rate may be small, maybe low, okay? But overall, the number is huge, right, compared with the geo network. So it implies that these two diffusion network indeed capture somehow different kind of diffusion pattern, okay, globally. And also we try to understand, okay, why the diffusion network look like this. Specifically, we'll compare the network topology of this diffusion network with the US rank. Okay, it's unavoidable with the US news ranking in the sociology program. So you can see here, okay, this is the x-axis, this is the rank of university, okay? And the y-axis, this is just in degree of on this diffusion network. And you can see the Penn State here, right? Penn State is kind of high in the in terms of the degree on the latent network. And you can see there is some kind of pattern, descending pattern between the rank and this in degree, right? And also this is the out of degree of the geo network and the latent diffusion network. So you can specifically, you can see compare with this geo network, there's very strong, clear pattern, okay, between this out degree and the rank. So the rank of this program indeed suggests some like influential, the degree of influential, okay, in terms of the diffusion, knowledge diffusion. Okay, so if your university have a higher rank and he have like stronger influence over the network. And this is kind of centrality. Okay, it's not that affected by the rank, but I just listed the top 3 university in terms of the betweenness centrality. The betweenness basically serve, you can think about a node with high betweenness centrality can serve as a bridge, connecting different parts on the network. So somehow you can Stanford, Cornell, Arizona State, okay, they serve as kind of a bridge, okay, on this diffusion network. Interesting. And also we check the PageRank centrality, another important index. So the PageRank centrality basically calculate like this, or the importance of node I depends on the importance of other nodes that connected to node I, right? So if you connected with important friends, then you're also important, something like this. You can see in this like a PageRank versus the PageRank centrality versus university rank, hence there is also kind of it's here. Okay, you can see it's about it's relatively high also. And this is like a preference. Okay, so overall in this kind of analysis, it's not very statistically rigorous. Okay, but we can see some like clear pattern that basically the latent diffusion network related to somehow the hidden knowledge influence, okay, among the universities. If you have like a program have high ranking, and typically it has like a stronger like PageRank centrality and higher like node degree. And specifically this relation follow the power law, okay? So few program typically have a very strong influence compared with other universities. Oh yeah, we have some simulation study to compare with some benchmark method. I think I just skip it. Okay. So just quick conclusion. So in this like a project, we defined a so-called double mixture cascading model to allow us to modeling the heterogeneity behavior in cascading, okay, in terms of both network level and individual level. And the good part is that I forgot to mention the whole the likelihood function is kind of a concave, which means we can provide statistically and computationally guarantee for the solution. And this method can be applied to other application. I think there's a very few some of interesting future extension we can consider to generalize this model to if you have a time varying diffusion network or like a field specific. The most important thing I think maybe it's interesting to see whether we can generate this association analysis to reach some like a causal conclusion under some kind of assumption. And computationally, it's interesting to see whether we can scale up this proposed method if we're dealing with a very, very large network with millions of nodes. I think that's it. Okay, thank you.
Well, thank you so much. We actually finished right on time. Yes. We can allow one quick question.
So, Musu, can I ask a question? Because I have to run. So,
okay, quick question. Yeah.
So yeah, I just want to see the network patterns AIJ. Is it engaged in the P, what is it called, TI given TJ? Is it engaged in those models?
I think that's a good question. I think in the model part, in the likelihood part, we do not have this A information. But when we try to estimate it, we do have remember the structure constraint on the
right. Yeah.
So that's where we
imposed that. But in the original one, even before your work, the previous one, did they engage the AIJs?
No, there's no AIJ. Yeah.
Oh, I see.
Yeah,
so just afterwards, you find that if they are geographically close.
Yeah.
I see. Yeah.
Yeah.
All right. Very good talk. Unfortunately, I have to run. So thank you.
Thank you, Yuan. Thank you for your question. Yeah.
Thank you.
Well, thank you all for coming. And if you have questions, please email Yubai or talk to him. So Yubai, what is your email address?
Oh, I can send to you again. Do you want me to send me now?
Yeah, just type on the.
Oh, okay. Yeah. Okay, I will text it here. So okay.
Type on the chat.
Okay. One. Okay. Yeah.
Okay, wonderful. Thank you so very much. And
okay.
well,
thank you,
everyone.
Mosaic.
Bye-bye.
Bye. Okay, bye.